So that being said, I want to start off with question 40, but not question 40. It's on page 40 here. That's why I said 40. This question dealing with illumination that, Eli, were you the person who had asked about it yesterday? Okay. That I'd never done it before, and I set it up, and I'm not going to relive the whole thing. We could spend a half hour talking about this. But I want to take us to where I landed. I developed the equation, and then what I ended up getting is this expression on the bottom left of your screen for the illumination. And we wanted a minimum illumination, so I differentiated it, and I got this derivative that is below it. And everything to the right here was just me reasoning out what the equation would be. So I started here, I developed that turned into this, and then I differentiated it. And I'll come back to that derivative in a second. When you follow kind of what I would call the rules of what you do with derivatives, which is to factor, to simplify, I factored out a -2, a k, an s, a 40 minus r to the -3, and an r to the -3 out. And I was left with this in brackets, 2r cubed plus 40 minus r quantity cubed. So then, of course, the parts with the negative exponents go below. And I'm pretty sure I had mentioned, yes, we have a critical value of r of 0, but r can't be 0. R was a distance from one light source to where you're standing. And we also have a critical value of r of 40. And I said, that's no good either. So I focused my attention on this. And I said, where is this 0? Now, there is a mistake here that I will reveal for you in a second, but I want to tell you the story of how we discovered it and how we fixed it. Shortly after the bell rang, Eli was here, Teague was here, there might have been a couple other people hanging around. It occurred to me that rather than expand this, do you remember me expanding this and getting a cubic polynomial and trying to set it equal to 0 and talking about that it's not factorable and you have to use Newton's method and all this stuff? It occurred to me that if this must be equal to 0, and it was like one of those aha moments. I said, wait a minute. If I move one of those terms to the other side and take the cube root of both sides, I'll get rid of the cubes. So I did that. I don't know which one I moved over. It doesn't matter. I'll leave it this way. And I said, if I take the cube root of that, and I think, you know what I think I might have done, is I arranged it so that this is negative and this is positive. It doesn't matter. There's a number of ways to accomplish that. One is you could move this term over and then divide by -1 or whatever, but you get that it's the same thing. So I took the cube root, and I ended up with the cube root of -2 multiplied by r equals 40 minus r. So then I said, well, we have to get r by itself. I'm going to add this r to the other side and get r plus the cube root of -2 r equals 40. And I factor an r out, and I thought, oh man, this is going to be so great if it works. And it didn't work, okay? But I'll show you why. And again, I want to tell you the story of what happened here. I factor the r out, and I said, I think at this point I said, so what's the answer supposed to be? And somebody said 17.7, I think. Does that ring a bell? And I said, oh man, if this works, and I could tell right away it wasn't going to work because 1 plus the cube root of -2, I know the cube root of -2, well, the cube root of 2 is a number bigger than 1. The cube root of -2 will be a number bigger than 1, but on the negative side of things, which makes the bottom of this a negative number, less than 1, and we're not going to get 17. And I went, oh man, I thought we were so close. And Teague was standing there, and Teague said, you know, if that were a positive 2, it would work. And he's right. If it's positive 2, it would work. And I went, oh, man, so what? Where'd that negative come from? Why? And then I think it was Eli who said, it was Teague as well, who said, the chain rule needs to be applied here. And I don't know if you remember, but when I differentiated this, I started writing negative dr dt because I thought, oh, related rates. And I said, don't do that. But you do need to multiply by -1. You do. Because the derivative of what's inside is -1. That makes this -1 times, well, the negatives cancel, basically. And if you still factor out a negative, you're left with a negative, which means there is no negative there. And if you follow along with that, you're going to get the right answer, it turns out. So I thought it was pretty cool that between the group of us, we managed to figure out what was wrong. This was a bit of a fluke because it had 2 things that were cubed. And it occurred to me later on that day that you could have also solved that. You could have also solved this by wrapping your head around the fact that this is a difference of cubes. It is a difference of cubes. It's a difference, where am I? There we go. Of 40 minus r cubed and the cube root of 2r cubed. And then here you're going to have the a squared plus ab plus b squared. But if we go way back to the beginning of the course when I introduced this to you, I told you this is never solvable. This second factor can never be 0, unless it hasn't been factored fully beforehand. So that means you can simply set this equal to 0 and solve. And you're going to end up with 40 over 1 plus the cube root of 2. Cube root. Anyway, I wanted to show that to you. And now I kind of have that in the back of my brain. If anybody ever asks again, I will know how to do it. Still an incredibly difficult question. So, take a look at your work, please. Does anybody have any questions you'd like me to go over, Jay? 9? The one right after? Okay. So, it doesn't matter what this is. I think this might be a pipeline of some kind. Oh, it's a railroad. We have 2 towns which are 7 kilometers and 5 kilometers respectively away from this road. And we're going to put a station of some kind at point S somewhere in between and connect the station with the 2 towns using railroads. But we want that distance to be as small as possible. The other thing you know is the distance between C and D is 6. And it's a case of maybe you can add too much to the diagram. I don't think we really need to add 6 there. We need to use that to do something like the following. Because we have to introduce an independent variable which we can use to describe the total distance from A to S plus the distance from S to D. And this is that cow problem, which if you think of it a certain way by reflecting one of these triangles, it becomes fairly simple to do. But with calculus, it's more difficult. What you can recognize is that this is a hypotenuse, and this is a hypotenuse. They're clearly different hypotenuses, but they are hypotenuses. And the length of this hypotenuse here, I guess I shouldn't just write that. What do you want to, let's call these P and Q. Okay. So in the triangle relating town A to that point S, the station, p squared equals 25 plus x squared. So p is equal to 25 plus x squared raised to the 1/2. Okay. In this triangle, q squared is equal to 6 minus x quantity squared plus 49. And that means that q is equal to 6 minus x quantity squared plus 49 raised to the 1/2. I'm using the Pythagorean theorem there. Hypotenuse squared equals other squared plus other squared. And that means that the total distance, I'm just going to choose to call it d, which we want to minimize, is the sum of p and q. I mean, I'm not sure you have to write p plus q. You could just go 25 plus x squared, quantity to the 1/2, plus 6 minus x squared plus 49, quantity to the 1/2. Now, I'm torn here, and I really don't know the answer to this question that I'm thinking. The question I'm thinking is it worth our time to expand out this 6 minus x quantity squared and add 49 to it right now? And I'm thinking, I don't really see why we need to do that now. We can do it later. Because right now, what we're after is a derivative. So when I differentiate, I get a bad choice of a variable, but that's okay. dd dx, and I wrap this 1/2 around the base, dropping 1 from the exponent and multiplying by the derivative of what's inside. And then I need to do the same thing for the other one. Boy, I haven't stopped and checked anywhere along here. 5, 7, 6, square root of x squared plus 5 squared, square root of 6 minus x squared plus 7 squared. I think we're okay. Now I need to differentiate the second term, and this is going to be 1/2 multiplied by the entire base, which stays the same, raised to the negative 1/2 multiplied by the derivative of what's inside, which is 2 times 6 minus x to the 1 times negative 1 plus the derivative of 49, which is 0. So now what do I do to solve this? I have two terms. I'm fortunate enough that this happens, so it's just one less little thing that I have to worry about is getting rid of that 1/2. I don't, on the face of it, I don't have any common factors. Right? When I take a look at this, I thought, oh, there's an x there, there's got to be an x here. There isn't an x over here. What there is a 6 minus x, but that doesn't contain a factor of x. But we still factor out negative exponents. I still need to factor out the 25 plus x squared to the negative 1/2. And by the way, that's going to go to the bottom. And 25, I hope I said plus, I might have said minus. 25 plus x squared can never be 0, so it wouldn't contribute to our solution anyway. However, very rarely does the denominator do so, period. I'm also going to factor out 6 minus x squared plus 49, and the exact same thing that I just said about to the negative 1/2. The exact same thing I just said about the factor of 25 plus x squared applies here. This can never be 0. This thing can never be 0 because then 6 minus x squared would have to be negative 49. And 6 minus x squared is something squared. Okay, so they're going to go to the bottom, and we're going to ignore them. What I have left then is my x out of the first term and a 6 minus x squared plus 49 to the 1/2. Out of the second term, I have a 6 minus x. I'm not going to make it. I have a 6 minus x, and I also have a 25 plus x squared to the positive 1/2. This is actually really good coming on the heels of that illumination problem, because we're going to solve this equal to 0 in the same way we solved the other one equal to 0 with the cubes, in the same general kind of way. Because you look at this and you go, well, the solution lies inside of this somehow, because those other two pieces go to the denominator, but they can never be 0. So are you okay with me not rewriting this so I can put these two to the bottom? Okay. I did. What Eli just mentioned is, did I forget the -1, which is that, and I certainly did. It's a recurring theme for me. And you know what would have happened had you not told me? We would have been in the same boat as yesterday, and I would have been scratching my chin going, man, I wish that had been negative, and then we would find it eventually. Anyway, so this, to find critical values of x, this must be equal to 0. But if that's equal to 0, since it's one term, since it's this term, not sure what happened there, my coat must have touched the board, minus this term, these two things must be equal to each other. This is the reasoning we're using. I mean, I could rewrite the whole thing and say equals 0 and then add one term to the other side. So now I have this. I have x times the square root of 6 minus x squared plus 49 must equal, nope. See, that doesn't look right to me, but I want to check. No, that's right. Just want to multiply it through. That will give me the 25 plus x squared and the x. That will, just be patient with me here. I want to make sure that it's good. It's just, there's a lot there, right? You got negative exponents, you got positive exponents. You got what was throwing me is there's a 6 minus x here to the 1, but in this it's 6 minus x squared. It's a tricky question. So the x times the square root of 6 minus x quantity squared plus 49 has to equal 6 minus x times the square root of 25 plus x squared. So this is my thinking here. And now I'm going to square both sides. Now I'm not claiming it's going to become, it's just going to, the sun will come out and we'll have some basic equation to solve. But it's going to be simpler. So I square this side and get x squared times 6 minus x quantity squared plus 49. I square this side and get 6 minus x quantity squared times 25 plus x squared. And looking at this, and I don't know exactly where it's going, but I'm asking myself, everybody, if I expand this out, what will happen? And one of the things that will happen is when I expand out 6 minus x quantity squared, I will get a positive x squared. And it's going to be multiplied by another x squared, which gives me an x to the 4 on the left. When I multiply out 6 minus, oh, well, what? Jeez. Why not? you can't do that. Why can't I do that? Yeah, that's too bad. I wish we could do that. So I do, but I notice I'm going to get over here x to the 4 as well. So I know it's not going to be a degree 4 polynomial. There is probably a very clever way to get to the answer from here, but I don't see it. So I'm going to expand this out. Why? Well, because we're here, so why not? Oh, this might clean up very nicely, maybe. Okay, there's my x squared. There's my 6 minus x quantity squared plus the 49. There's my 6 minus x quantity squared times the 25 plus x squared. Okay, well, let's just power through and see what happens. 36x squared minus 12x cubed plus x to the 4 plus 49. Oh, I guess I could have added the 36 and the 49 together. Does that look okay? A little bit more work here. 36 times 25 is 900, but you better double check that. Pretty sure that's right. 36 times the x squared is 36x squared.
You missed the square.
Yeah, no, I'm just looking. I think this is going to, it won't. So I'm done with the 36. Now negative 12x times 5 is negative 300x, but I need confirmation on that. Looking at this product. Good. Negative 12x times x squared is negative 12x cubed. Oh, that's nice. That relaxes me a little bit, because the cubes, I believe, are going to be gone. I'm done now with the negative 12x. X squared times 25 is 25x squared. X squared times x squared is x to the 4. We'll just throw that there. So we have the equal sign here. Gone. 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 The x squareds don't go away completely, but there's 36 that do. All I have left on the left-hand side, this is one of these ones where I kind of joke, but kind of serious. If this works, it'll be a miracle, right? 49x squared equals, what do I have? 25x squared minus 300x plus 900. That's what I have. I'm pretty sure 24 doesn't divide into 300, but I know 4 does. Does 12? Does 12 divide into 900?
Yeah, 700.
But 24 doesn't divide into 300. No. Okay. So I can take out a 12 to make my life a lot simpler. What is this, 15? 25. I couldn't tell you. 75. Okay. If this is factorable, I'd be blown away. Is it? That's.
I'm pretty sure if I put it in right, I did the.
If it's factorable, I think we've got it. Because usually these questions, if the solution to this is not a rational number and we happen to stumble on a factorable quadratic, I think that's a fluke. So what did you get for a discriminant?
1,225.
For this? Can you repeat that?
1,225.
And that's a perfect square?
Yeah, 35.
Okay. So it's factorable. I'll give it a shot. I'm not a big fan, and I'm not very good at factoring when we have bigger numbers like this. 75, I'm thinking 15 and, but it's negative. Well, 15 and 5, 15, 5, 15. Yeah, I think I got it. Holy smokes. So in the context of this question, your two critical numbers boil down to 1 and only 1, which is in the domain. So I'm hoping that the answer is 2.5, 5 over 2, away from C. Okay. Okay. Other questions? And I'm never afraid of a challenge, and I'm never afraid of making a mistake. Neither should you be. Seriously. This is brutal stuff sometimes. Other questions? Go ahead, Craig.
8, which is the previous question.
Okay. We used to learn how to find the equations of these. That's the equation of an ellipse, of this ellipse. And we want to maximize the rectangle. So the first thing I would say to you is I don't like the fact that they drew this rectangle kind of squarish. The rectangle could be any rectangle that you can inscribe in there, right? It can be very long and very short, or it can be wide, not as wide, but taller. Right? And there's a way to, and Cyrus, this is like the question you and I were talking about a little while ago today. There's a way to make this easier, because if you're trying to maximize the area of that pink rectangle, then what we need to do is maximize the area of this rectangle. If we make this rectangle as large as possible, and all 4 of those rectangles by symmetry are equal, you do need to know that this is a symmetrical figure. I think you suspect it's symmetrical because of the x squared and the y squared. Whether it's positive or negative for x, those squareds remove it. If we can maximize the area of that, we will be maximizing the area of the whole thing. If you were asked for the maximum area of the whole thing, then we can find the maximum area of this and just multiply by 4. Okay, so we need a formula relating that area to some variable. And it's this. Because this curve, every point on this curve has an ordered pair. And the connection between the ordered pairs is up here. So x has a particular value. X has a particular value here. Get rid of that. And y has a particular value. But when you square x and add 4y squared, you're going to get 4. And when it is here, you're going to get 4. So this point has an x-coordinate that's the width of this rectangle and a y-coordinate that's the height. The only difficulty here is we have to get rid of a variable. I would recommend getting rid of y, because I think there's nothing more confusing than having a bunch of y's over here for the independent variable. We're going to get rid of the y here, Craig, by taking this equation and rearranging it for y. So I can divide everything by 4. And then take the square root. So y is going to be equal to 1 minus 1/4 x squared to the 1/2. Minus 1/4 x squared to the 1/2. Which means this becomes x 1 minus 1/4 x squared to the 1/2. And we're ready to differentiate. Yeah, we'll differentiate from here. I was throwing around the idea of writing the x outside as the square root of x squared. So then I could put that x squared inside of the square root, the other square root. But I don't think doesn't really do anything. Well, I've got a lot of space here. I'm going to have to use the product rule, where this is the first and everything else is the second. So derivative of the first times the second plus the first times the derivative of the second which is that. And I hope I'm not alone here. I hope you're all doing the math too and confirming that that's correct. Does that look okay, Alex? Anybody else willing to go along for the ride here? Okay, good. Thank you.
1/2 x negative.
I left that out to see how many of you I could catch. Yes, it is negative. Good job, Alex. Oh, the calculus shame. Are we okay with it now, do you think? See, but we're smart. We're a smart group of people. And many of us miss that. It's also Friday afternoon, and maybe we have other things on our mind. Okay, now I'm going to factor. Well, I shouldn't say that. I want to cut a corner here and take a shortcut, but I better not. We don't have to, but it's nicer to get rid of those fractions. Okay, you could leave them in and grapple with the fractions later. I prefer here to say, you know what I'm going to do is multiply the top and the bottom by 1/4. I'm not talking about getting rid of this quarter in front of the x squared or this quarter in front of the x squared. I'm talking about getting rid of this 1/2 and this 1/2 that are outside of those square roots. So now what I end up with is 4 times 1 minus 1/4 x squared to the 1/2 plus minus x squared times 1 minus 1/4 x squared. Well, that's nice. That's weird. Isn't that weird? That these terms each have, oh no, because it was the product rule. Never mind. So now that I've, we're multiplying the top and the bottom by 4, right? Not 1/4, by 4. Okay, so I've got the 4 on the bottom. I have this times 4, which is 4 times 1 minus 1/4 x squared to the 1/2. These two halves are gone. My negative is here. I have x times x, which is x squared, and I have this other thing raised to the negative 1/2. I'm pretty sure that's fine. Yeah? Yeah. I think it is. I really do. Okay. So I can factor out 1 minus 1/4 x squared to the negative 1/2. I always take out the negative exponent. I'm left with 4 times 1 minus 1/4 x squared to the 1, because these two exponents here have to add to give the exponent I started off with. Minus x squared. Looks good. Again, the solution is going to lie in this. This part that's going to go to the bottom will have critical values of x. If I had to guess the critical values of x, the values of x that make this equal to 0 are going to be the end points of the ellipse or the top and the bottom points of the ellipse, thereby giving you no rectangle. Okay? So if I just solve this, I have 4 minus x squared minus x squared. I'm expanding this out. 4 times 1 is 4. 4 times 1/4, x squared is x squared, and I'm subtracting. So this factor is 4 minus 2x squared, or 2 minus x squared with a factor here of 2. And this thing on the bottom. I'm kind of not following a very rigorous path here, but does that look, do you understand what I did there? Okay. Which means I have, let's do it. I have critical values of x of plus or minus root 2 for the numerator. And if I take 1 minus 1/4 x squared and set it equal to 0, multiplying both sides by 4, I have critical values of x of plus or minus 2. But 2 is the x-intercept. So plus 2 will give you no rectangle. In other words, the domain here, everybody, for the way I've set this up is that. It has to be greater than 0 to be in quadrant 1, and it has to be less than 2 to get a rectangle. So the only value that's critical for x that makes sense is root 2. You know, the first time I saw one of these questions, I couldn't wrap my head around it because my brain kept steering towards related rates because there's speeds involved, right? So a boat leaves a dock at noon and heads west. So we'll just say that this point is a dock, and one's going to head north, so I'm just going to draw this here. One heads this way, and it travels at 25 kilometers per hour. And one heads north, and it travels at 20 kilometers per hour. So in terms of motion, the one moving west is traveling faster, the distance will be greater. Now, again, I have to really focus because I wanna think about the rate at which the distance is changing, but that's not it. That is not what we're doing here. What you want to do is find out, oh, my mistake. Second boat is traveling this way. Okay. And we want to find out, noon, 1, we can add something into this diagram. Okay. And it's that if the boat traveling north reaches the dock at noon, it must have started 20 kilometers south of the dock. Because it's going north at 20, and from noon, or at 1, and from noon to 1 is 1 hour. So this, from where this boat starts, this distance to the dock is 20 kilometers. Now, I don't know if we will need that, but I just realized we will. So these two dots are where the boats start. We're interested in a variable kind of situation here. So I'm going to put, doesn't matter. I'm going to put these two green dots to represent where they are at any point in time. At any point in time. And that means, everybody, that this greenish line is the thing we want to minimize. And it's a hard thing for me to wrap my head around to even say, you mean there's going to be a minimum distance? But when you think about it carefully, when they first start, they're going to be getting closer together. But sooner or later, they're going to be getting further apart, right? I mean, they have to be, because the westward boat will be way, way, way far away to the left. I don't like that line. I don't like the color. Bothers me. Okay? You too? Good. So how do we define that distance? Well, this distance, and the first time I saw this, it took me a while to figure out what to do. This distance is 25t. It's 25 kilometers per hour multiplied by however many hours we're talking about. And this distance here is 20 minus 20t. This is 20t. 20t is the distance that northbound boat travels in t hours. So the distance above it is 20 minus 20t, because the whole distance is 20. And the reason why I'm finding that little distance is the solution lies in a Pythagorean relationship. We can define this length in terms of another variable, t, so we can find dl dt. And finally, I get the chance to show something to you that's a real lifesaver in terms of work and the amount of work you need to do. If you go L equals the square root, I better not do that. L squared equals 25t squared plus 20 minus 20t squared. That's the Pythagorean theorem, yes? Okay. I'm just trying to decide whether I want to show something to you or not, and I guess I will. All right, so that means L is equal to 25t squared plus 20 minus 20t squared to the 1/2. And this is what we need to differentiate. So I'm going to find dl dt, and my first step will be to do this. And then I need to multiply by the derivative of what's inside. Are you with me on this?
Should it be a 1/2?
Yeah, it should be a 1/2. Thank you. So you're with me on this? Okay. We're going to multiply by the derivative of what's inside. But this whole leading thing, except for the half, has a negative exponent, which is going to put it on the bottom where solutions don't reside, or very rarely reside. Okay? And by the way, when you put this on the bottom, it can't equal 0. Right? Let me write that out for you. That we're going to have on the bottom a 2 and a square root of 25t quantity squared plus 20 minus 20t quantity squared. That's what we will have on the bottom. There are no critical values of t associated with that because that can't be 0. And the reason it can't be 0 is both of these things that I'm going to underline are going to be positive or 0, but they can't both be 0. Right? One can be 0 or the other, but not both. So that will never be 0. So keep that in mind for something I'll show you in a few minutes. Okay? This is not relevant, this part. What will be relevant is the derivative of what's inside, which, I mean, you could certainly, I think 25 squared is 625. You could certainly do it that way, but I'm going to write it as 25t raised to the 1 times the derivative of what's inside, which is 25. I'm wrapping the exponent of 2 around the 25t. And then plus 2 times 20 minus 20t to the 1 times negative 20. Yeah.
It should be 2 times 25. It should be 2 times 25.
Okay. So this thing, which by the way is linear, right? It's not even quadratic, it's linear. It's pretty messy right now. But if we simplify it, we get, rather than factoring out some of those numbers, I'm just going to simplify it first. Then we'll worry about the factoring. 25 times 25 is 625. Times 2 is 1250 t. Minus 2 times negative 20 is negative 40. Negative 40 times 20 is negative 800. Two times negative 20 is negative 40 times negative 20t is positive 800t. Steph, I did that in my head, so can you confirm? Yeah, it is. It's 800. So this is negative 800. This is negative 800t. This is 1250t. I don't think we need to worry about factoring. This is 2050t equals 800. You could certainly start factoring. 2050t equals 800. Moment of truth. Oh. Does the question say what time? Let's see. When were the boats closest to each other? So, I mean, could you imagine, by the way, just to take a breather, could you imagine now having to do a first derivative chart to confirm that this is a minimum? $12.23. That's 3 in a row. But I want to show something to you. Do you see how I got to 23 minutes? What I'm doing is I'm getting this 800 over 2050 being 0.39 hours. And I multiplied by 60 to find out how many minutes it was. Do they give the answer as like 1223? Is that what they say?
They give it as the number of hours and
Okay. But that's the right number. Okay. So I want to point something out to you now. And this is something I remember from when I first learned calculus a long time ago. And I'm assuming it's okay that this is the reasoning. This is the reasoning, and there's a slight flaw in it, but we are trying to minimize this. We are trying to make this as small as possible, right? But this is the reasoning. And if you can find the flaw in it, that's fine, but it will always work. If this is as small as possible, then this must be as small as possible. In other words, instead of minimizing L, why don't we minimize L squared? Why don't we minimize the square of the distance? Why don't we minimize that, which is the square of the distance? Well, you will notice something, that the derivative of that is that. Right? There is none of this garbage that's in front because we ended up taking the square root, and that garbage in front goes to the bottom and is never contributing to the solution anyway. So when you are ever asked to minimize a distance that is a length of a hypotenuse, and you have hypotenuse equals a square root, if you want to minimize that, just minimize the square of the hypotenuse. And it makes your life a lot easier. So find the point on the parabola 2y equals x squared that is closest to a particular point. By the way, this parabola is also known as y equals 1/2 x squared, right? The reason why most students in calculus in high school in Alberta will look at this and go, I don't really know what to do, is we used to teach in Math 10 something called coordinate geometry. And we used to teach that anytime you have 2 points, the distance between the points has a formula. And the formula happens to be this. And I suspect that once you see this and once we start talking about it, you understand that this is just about the Pythagorean theorem. But without seeing the formula formally and without being taught about it, you kind of tend to lose the strategy that you can use here. It doesn't matter how I draw this triangle. It doesn't matter how I draw it. It is a right triangle as long as I talk about x and y coordinates. And the base of this triangle happens to be x2 minus y2. And the height happens to be, the base happens to be x2 minus x1. And the base happens to be y2 minus y1. Have you been taught this formula before? Yeah, I don't think they teach it to you anymore. It's just been so long since I've taught a grade 10 math. So when we take a look at this, excuse me. When we take a look at this, here's 1/2 x squared. We know it goes through the origin where the vertex is. And we have a point, -4, 1. By the way, over at -4, 1, the point is below the parabola. Not that it matters. It doesn't matter. And the reason it's below the parabola is when you put in -4 here, you get a y coordinate of 8. So what we are trying to do is, I hope you would agree that this point will not give us the minimum distance. And this point will not give us the minimum distance. It's going to be some point in here. But it doesn't matter where it is because we're going to use the distance formula. Well, I'm going to use the Pythagorean theorem. Here is the point x, y. Here is the point -4, 1. The base of this triangle is 1 minus x, or -4 minus x. And the height is 1 minus y. I hope you see it doesn't really matter the order in which you subtract because you're going to be squaring them, right? So I guess I'll write it this way. So I'm taking x and I'm subtracting -4, which is x plus 4, which will give me this distance. I'm taking y minus 1, which will give me that distance. That's supposed to be a right triangle. And I have that. Now I do need to get rid of the y. But I can substitute in for y 1/2 x squared because every point on the parabola has a y coordinate of 1/2 x squared. Perfect opportunity for us to do what I just explained to you. Let's not take the square root to minimize d. Let's minimize the square. Let's minimize the square of d. Are you with me on that? Okay. So now I can differentiate the derivative of the square of the distance with respect to the x coordinate of our answer. WD-40, just you'll be done. Well, it's still going. There we go. So I swing the 2 around the x plus 4, drop 1 from the exponent. If you like, multiply by the derivative of what's inside, but what's inside has a derivative of 1. Bring the 2 down in front of the 1/2 x squared minus 1, which stays the same, drop 1 from the exponent, and then the derivative of what's inside is x. I don't really see the point in factoring that 2 out. If you want to stick to the rules, you're supposed to factor, but why bother? It's just a basic quadratic. Let's expand this out and see what happens. I get 2x plus 8 plus this 2 times this x. Oh, it's not quadratic. It's going to be cubic. Well, that's unfortunate. Is 2x times the 1/2 x squared is x cubed. That's a real drag. No, it's not. Because when we expand it further, we get negative 2x. These two terms reduce to 0. Which tells me that d square of the distance dx is equal to 8 plus x cubed. If you want to factor that as a sum of cubes to discover that x equals the cube root of negative 8 or negative 2, be my guest. But if you just set it equal to 0, you get x cubed equals negative 8. So x is the cube root of negative 8, which is negative 2. So the x coordinate of the point that's closest on the parabola, that's closest to the point negative 4, 1, is negative 2. And then to find the y coordinate, we would put that in for x and get what I believe will be 2. So there's that point. There's y equals 1/2 x squared. I guess I'll put in the other point, negative 4, 1. Okay. Whoops, no. 2, negative 4. What a dumb system. Okay. And I'm just going to graph. I'm going to go zoom square. The reason is, well, I'll go zoom standard again. And at first I thought, uh-oh, something's wrong. Do you agree that point does not look like the closest? That, if I connect this point that we found, negative 2 comma 2 to that point, it looks like there is a closer distance here. That's because it's scaled differently horizontally and vertically. It's skewed. So that's why I went zoom square. Let's see, zoom square. And it looks reasonable now. Is that okay?